Alright, response video to Hotler Days. This is just for Hotler Days, so the rest of you don't have to pay attention. But he really is so obnoxious. I mean, he doesn't really need to be for this argument, but he just puts words in my mouth that don't belong there in terms of, like, I'm arguing intuition versus science or something. That's not what I'm arguing. I'm arguing that science has to be better than this. So we're back. We're still on the two-slit experiment. Alright, so he's claiming that, okay, the experimental results show that when one slit exists, this is the pattern. It's just this, basic sine wave, blah, blah, blah. And, when there's one slit open in a two-slit experiment, right? Okay, well, here's the results from something posted by somebody else, and let me enlarge this if possible. Yeah, it's possible. At least it says it's possible. Oops, I gotta remember I switched the mouses. Alright, so we'll go up. Whoops, it's still enlarging. How do I stop it from enlarging? I don't want it any larger, thank you. Alright, so this is one slit open, I believe, yes. Okay, so you can clearly see this is one slit. We clearly have pattern. Okay, we have the dot, 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 dot. Alright, so this isn't happening. We are getting dead spaces, clear dead spaces. Now the question is are these additive from left to right? So this was the one slit on the right and then left, and then we can go to the right and have the argument about what we see. So this is with an experiment where you cover the slits with another material after the impact. Okay, now this is my argument, okay, which you didn't address any of my arguments, okay. Key to my argument was the double slit experiment depends on, okay, this middle material. Do you see this thing in the middle? Do you see this thing in the middle? Alright, that's a smaller piece of matter. This is a big wall. This is a big wall. Get it? And this is a little tiny, 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 tiny wall. Little tiny, 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 tiny thing. Okay, in the middle. Alright? So let's not talk about one slit. Alright? Because there is no such one slit that you can make with tiny, tiny, tiny thing on one side. Right? You can't make a one slit experiment with little tiny thing on one side and big wall on the other side. Now can you? Can you do that? Can you make a one slit experiment that way? No, you can't. So there's key point number one you ignored. That was in my video. Key point number two that you fucking ignored. Alright? I mean, it's just annoying. I mean, I drew this shit. I talked about this shit. I said this shit. And you just ignored this shit. Now, if you're going to have a one slit, two slit experiment, right? Now, say this is the two slit experiment. Now we'll do over here a one slit, okay, experiment by how you diagrammed it. Now, you diagrammed it that the light comes in a cone with a let's just draw it as a cone, okay, and that's the way the light is coming into the slit, right? That's how you claim that's what's happening in the one slit experiment, and that we would expect the same kind of thing just spread out a little bit on the receiving surface, the same cone of brightness. Alright, now the problem is, okay, when you go to one slit, is that your initial cone is in a different position. So for the one slit to duplicate that, if you're going to duplicate it with just one slit, you have to duplicate the light as it enters the same way over here. So it's half the cone. So the cone is here. Alright, the position is different. So the light distribution is not even to the center. The light distribution has its peak right at one of the slits. Right at the barrier. And so it is this half of the cone that's going through the slit, and you would expect, like this pattern, that seems quite rational. That an uneven cone would give you that kind of distribution. It would be weighted on one end, and it's weighted on one end. So that's another point to be made. Let's also understand that you drew the wave pattern like that. Now, we know that's not the pattern we receive in a two-slit experiment. The pattern in a two-slit experiment is this pattern. Okay, very different. So yes, this is wave interference. Okay, because wave interference ends up with a even distribution of density at each point. So if it was a water wave, the interference bars would travel out in a radius, something like that, and the high points and low points, but they would be, their distribution would end up even. Like you'd have a double here, two highs to one low. The wave can never go to 16. So this is the representation like glass: 16, 8, 4, 2. Okay, this progression, alright, is the interference pattern in the two-slit experiment. It's not the same interference pattern. Yes, it has the same low spaces, okay, dead spaces, so it has the same zero spaces, but it doesn't have the same distribution in terms of the intensity. That's because this light does have a higher density of impact. A higher percentage of the impact will happen on this peak. When the lights, there's more light here than there is here and here combined. Alright, and that's the truth of this pattern, unlike a wave where the distribution is evenly spread across the wave front. So that's another inaccuracy in your portrayal of the results received, and you would have to explain why there's this intensity difference if it's just interference between two equally distributed wave fronts. So, key point, the center impediment is much smaller than the two external walls, creating a different electromagnetic potential. The focus of this light has been concentrated. Again, I said it right there. This is the bullseye. Okay? Very little light. I said maybe 90% of the light is in this circle. It doesn't get over here. Only 5% and 5% might ever go in impact on these external walls. That's how the two-slit experiment I'm saying is being done. The focus of the light is here on the center impediment, not on the external. The external walls are unnecessary. You can create an interference pattern without the two walls by just using a pin or a needle and shining a laser at it. People have done that on the internet. And that's how the experiments are done. So again, you have to acknowledge that a true one-slit experiment, if you were going to duplicate it as it's done in this experiment, you would have to shift the focus of the light off-center. And you'd have to hit just one of the slits with 90% of the light. I mean, one of the sides would end up getting 90% would go here, and only 10% would do this, interact with this other slit. If you want to duplicate the real circumstances of the double slit experiment as isolated single slits. Now let's go, the last subject is the stupid detector crap. So he's claiming that they have technology capable of detecting an electron precisely enough to the tolerances of the thickness of this slit material, which I thought was supposed to be something like 200 and something nanometers. Maybe it's multimeters. Multimeters, is that it? Yeah, well, whatever. It's very small. So I don't have the actual dimensions. It would be nice to have all the dimensions, right? I mean, there isn't that many dimensions to these experiments, right? If we had the slit width, the thickness of the material, the length of the focus, the length from the gun to the focus, the aperture that this light's coming out of. This is an aperture here, remember, you didn't have that in your diagram, was the aperture creating the light, and the distance to the target. I mean, these are all kind of important. Another thing to recognize, another feature to recognize, is that water waves wouldn't have a focus. You would see the interference pattern once you're far enough into the wave. You would see it at any focus. It have very long focal length. All you do is spread out the bars. The bars would get further and further apart. The bars of double would get spread out. Unlike this, which seems quite dependent on focal length. So anyway, yeah, the detectors. So anyway, the idea that you can construct a detector for electrons that's precise enough. Again, we're back to this precision argument, right? The more precise your measurement, the more aggressive your interaction with the particle has to be. So you have to demonstrate to me that the tolerances to detect an electron passing through the thickness of these slits is sufficient. You can do that with sufficient precision without interfering with what's happening in the neighboring slit. That you're not creating any kind of electronic noise in your effort to detect that would disturb that reality. The other fact I think you have to consider is, again, if your source of electrons is now off-center and you put your detector in the center of the slit, okay, can you see how that might create a problem? That your source is off-center because you're duplicating the light source in the two-slit experiment. And if your detector's in the center of the slit, then it's going to be likely that the detector will force a straight, that it will straighten its path rather than crooked its path. The likelihood is it's going to take off the angular momentum and create a new angular momentum straight through the slit. That would be the function of the detector, essentially, would be to destroy whatever angle of incidence coming in and create a common result leaving. So it's not like it's going to add chaos. It's going to do exactly the opposite. The detector is likely to take the chaos off. It'll take whatever individuality these different photon streams had and convert them into one straight path, a common path. So it's not going to add chaos, it's going to subtract chaos. Chaos meaning ranges of probability. It's going to limit the probabilities, not expand the probabilities. So what else? Yeah, well, that's probably, and so there's no point in even discussing experiments where they turn detectors off, because I've never seen one. I don't believe they exist. I think it's absolute nonsense. It's silly talk. It's absolutely crazy. It's kooky. How can you even say anything? The tape machine registering whether I saw an electron or not would be external to the experiment. It's completely external. There's no way it could have an impact on the experiment. There's no way the photon could know the tape machine's on or off, or whether the tape machine has tape in it. It's a ludicrous proposition that you are forced to find a better explanation. It's as ludicrous as just inventing Thor to explain thunder. It's ludicrous. There's probably some better explanation than a giant rabbit scratching its ear in space. And that's what that crap comes down to. It's absolute shit. And you referenced the NOVA program, which I've already mentioned is crap. I already did a video years ago on it, I'm pretty sure, but it's just a horrible... They described this using bowling. That's how they described this, with a bowling metaphor. I mean, you're still not getting it. I mean, you're really not getting it. You keep talking about whether these are discrete particles. That's not the argument. The argument is whether the matter that it's interacting with is solid matter. If it's something actually bounces off of it, like it has a solidness, that it's not made of electrons, and that the electrons are interacting with the photons and re-emitting photons to create the reflections and the diffractions. That the photons leaving the two-slit experiments, right? The ones that go into the two slits, I think Feynman might tell you, okay, the photons going out might by some 90% number not be the photons that went in. That they actually did react with electrons and were re-emitted at a new angle. That's the whole point here. The matter's doing it. And you're not accounting for the matter. You just want to keep talking about bowling balls and bullshit. Okay, again, it doesn't even matter whether photons are actual solid, like round little ball or something. It doesn't matter what the photon is made out of. The argument being made is, where is it in space and time? And does it have a place in space and time? And some other asshole brought up the math. And again, Susskind will tell you that yes, you can reverse engineer the math. There is no location on this wave that you can't reverse engineer back to the source. So it's not like it has to go in 14 different places to get here. No, it has to stay within the confines. Particles can't go over here and end up here. That's not happening. The math indicates they do exactly this. They refract off the material, or they deflect off the material. But that's the math. What else? Well, this is really enough. Again, stay focused on the thing I'm making the distinction. I'm arguing that 90% of the interaction is with the center impediment. It's not really a two-slit experiment. It's a single impediment experiment, or a single pedestal experiment. And you can't do a single pedestal experiment measuring only the impact of one of the sides to the pedestal without acknowledging that changes the focus of the beam, and without changing these other parameters. And again, these results indicate one slit here, open, lots of interference pattern. Okay, and if we go down to the other side, I have to do this with the fingery thing, which is annoying. I have to grab it and pull it up. That's it. So see, this is how it's not really a great two-slit experiment. So you can see that there aren't real good divisions here, but obviously there is more intensity at the center and less at the external. And as they cover the other slit, which isn't done perfectly sequentially in the measurement of time, clearly you can see again we have the pattern formed. That's correct, right? It looks like the same size. Yeah, I went the wrong way. I need to go this way. Up, 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 up. There we go. Well, see, I put them next to each other here. So you can clearly see it here when they're next to each other. Okay, the two longer tails here on the sides. And then when you combine these two patterns, that you might end up with something very similar to this, because you can see the slight bulges here. Those bulges will be magnified when you superimpose them on each other, and you know, you can even see the alignment of them here. That one aligns, this one pretty much aligns, this one aligns with this one, this aligns with this one aligns with that, and so the brightnesses will intensify and the dead spaces will remain existing, and you'll end up with something that's maybe 70 or 80% what you have there. I mean, this is the most, well, there's no point in making a point out of it, I suppose, but you can almost see a difference in the clarity of these different images. which is kind of strange, you know, depending on how open the two slits are. They're very similar, but there is some distinctions, you know, even though they're very technically they're both open in this circumstance. It almost seems like there's a little bit better division when there's a partial interference with something. But anyway, it's a minor amount. So anyway, enough. I don't want to beat it to death. So take care of the pedestal idea, the fact that the focus is on the pedestal, the light is focused on the pedestal, that this is the target zone. This is where the light goes. Here. Not here. Okay? Here. It's inside the two slits. The focus. Not outside the two slits. There's not an even distribution of light going through the slits. The light going through these slits is not all just even. Same amount of light through each area of the slit. There's much more light at this end than there is at this end. And that just happens to be the pedestal end. And that's important in terms of maximizing contact with electrons. And electrons change momentum, direction. There we go. I've done my job.